Yeah, then let's get started then, because again, much like the last presentation, we have a lot that we're going to cover in this one. So are the recordings rolling? Arpin, are we
Yep,
recording?
ready to go.
All right, all right. Let's start off then. All right. Thank you everybody for coming to Honeybee Energy Modeling Part 2. This is and I'm going to start this off with just sort of putting it into context where we are in terms of the whole series. There's actually, and we have a slight change of schedule that I just wanted everyone to be aware of, particularly because we realized there was just so much new stuff to cover in Honeybee Energy Modeling, stuff for which there isn't really any video tutorials right now, for which you guys are really the first to see them, and so we've decided to sort of have two more sessions on Honeybee Energy Modeling, including this one. So just to give you guys sort of heads up of what's going on here. So we covered sort of this somewhat basic introduction to energy modeling just with a single zone this past Thursday, where we reduced the heating energy use of an office and cooling to some extent for an office in a cold climate. We worked mostly with just some very basic facade strategies, and we used the energy balance to help inform what were the areas that we really need to focus on to get the heating and cooling energy use down. And today we've decided it's going to be all, just because there's so much to cover in this, we're going to make it all about HVAC and metrics that are output by energy simulations with HVAC, like utility costs, EUI, and we're going to really understand, we're going to get deep into understanding how the selection of an HVAC impacts the energy, the final energy use of our building. And this is going to be also, I'm going to introduce everyone to, the first time, the brand new really workflow to work with OpenStudio, which is OpenStudio being the interface for building energy models that Honeybee is linking to and building off of. And we're going to visualize some HVAC systems using OpenStudio and discuss some of the different workflows that are now available now that Honeybee has a strong connection to OpenStudio, which really only came to fruition within the last year or so, as OpenStudio really started to be really developed, and a lot of the issues really with OpenStudio have been fixed. And then so today is only going to be sort of about HVAC and those types of metrics. We're going to take a bit of a break for Thursday, just because we've been kind of running a marathon with every single Thursday, every single Tuesday the past 3 weeks, and I think maybe just a break from everything might be. Would be merited. And then finally, we're going to pick up Tuesday, and we're going to finish off energy modeling and comfort. And specifically, we're going to focus a lot on comfort during this session. We're going to go over some newer workflows for which, again, both this session and the session on Tuesday are going to have workflows for which there are no currently available video tutorials on them right now. And we're going to work with the adaptive comfort and a few different strategies for eliminating cooling systems in hot climates, sort of contrasting with the model that we have been working with in a cold climate with an office. And then I'm going to show you guys, with a full session on it, I'm going to take the time and show you guys how to make detailed microclimate maps, which are something were the result of my thesis and are integrated in Honeybee. And importantly, not only are there not any video tutorials yet on the microclimate maps, but it's one of the things that is only available really in Honeybee right now. And that there are a lot of interfaces that will give you really detailed, spatially detailed maps of comfort, but they'll only be for a single point in time or a few points in time. And there are also a lot of engines that will show you over a long period of time what the comfort is like, but they'll only give it to you at a single point in space. And these microclimate maps are really one of the only things that cover such a broad range of both time and space, where you get really high resolution visualizations of microclimate over long periods of time. And for those of you who are familiar with the sort of the daylighting metrics of like daylight autonomy and UDLI, we're going to sort of, these microclimate maps enable a similar set of metrics, but for thermal comfort, and that's what we're going to go over on Tuesday. Sort of visualizing the number of comfort hours over an entire year spatially. All right, so getting back to today, we're covering HVAC, as I said, and specifically I'm gonna go through, as opposed to usually we have a longer segments of longer examples, and this session I think is going to be much more about, because it's really the first tutorial session on HVAC and OpenStudio that we've had for Honeybee. It's going to be much more showing of sort of the capabilities, how to do certain things. I mean, we're going to also be using a design example and trying to improve that, improve the HVAC of it. Specifically, we're just going to use that same file that we used last time of an office in a cold climate. But really, a lot of this is going to be geared towards showing you exactly how to use these things and pointing the way towards, especially a lot of advanced users, so that you're able to run really simulations of pretty detailed HVAC. And specifically, I'm going to first start off because everything we worked with last time had to do with an ideal air system, and I'm going to talk about sort of when that assumption is and is not okay, when you have to switch over to a detailed HVAC energy model. I'm going to talk about the sort of 14 HVAC templates that Honeybee currently has. I'm going to walk you through a Grasshopper file with that, and then we're going to use that to visualize and calculate utility costs and end-use intensity, or EUI. We're going to do that in Grasshopper so that you guys will have a means of really quantifying to clients and people exactly how much each of a given energy saving measure, how much that would save. And then we're going to visualize some of these HVAC systems in OpenStudio. I'm going to introduce you guys to the OpenStudio interface. And then we're going to we're going to spend a good chunk of time in a design exercise of just improving HVAC parameters in Honeybee and testing out a few different HVAC systems. All right, and then finally at the end, I'll just show you guys quickly, just so, this will be a sort of pointing to the open-endedness of what you can do. I'll show you how to, that it's possible to edit the HVAC systems in OpenStudio, edit the model in OpenStudio, and then rerun it in Honeybee. All right, so with that, I'm going to jump right into the sort of this sort of first bullet that I have here. But I will just say again, a lot of you already kind of know, but we're working just with Honeybee today, and again, it's just these energy components. For both this session and the next session, we're going to be working with OpenStudio and Energy Plus, pretty much, and only after that we'll go into the daylighting and the therm plus window connection for the last set of tutorial videos in the series. Okay, so to jump into the first part of the presentation, of just explaining what exactly, well, even before we explain when the ideal air assumption is okay, it's probably first just important to highlight what are the differences between these two types of simulations that you can run. So everything that we ran last time was with this type of HVAC system, the somewhat simplified type of HVAC system called an ideal air system. And just so that you guys understand, what are the key differences between that and modeling a full HVAC that has fans and pumps and boilers and chillers and everything that really consumes energy. And we're just going to run through some of the key differences that are really important to know. Again, actually, and this is just reiterating what I said, we used this last time, ideal air, and this is what we're going to use this time. We're going to use detailed full HVAC systems. And so ideal air systems, the values of heating and cooling that you get out of the simulation, if you guys remember, those are just the energy that is directly added or removed from the zones, directly added from to the rooms, basically, of the space. And that's what makes our energy balance when we look at how much heating and cooling is needed in the space. That's why the outputs of the ideal air system were matching, such that we always had the heat going into our building equal to heating out, because that heating and cooling is just the energy added or removed from that space. Whereas when you model a full detailed HVAC system, the heating and cooling values that you're usually getting out of this, they aren't really that direct energy added or removed from the zone, but they're the fuel energy or the electricity that are being used by the components of the HVAC system. And so it's important that this is very different than the heat that is added or removed from the zones, because electricity doesn't, necessarily translate one-to-one into cooling energy. That a lot of times for a given unit of electricity, there's this, you'll pull out actually much more heat from the zones of the building. And fuel operates a bit differently, that usually not all of the fuel that you burn is able to get into heat energy in the space. So that's the first most important distinction between the two systems that we're going to be, between what we did last time and what we're doing this time. Secondly, the ideal air system, it's always going to be reporting on a zone by zone basis, that heating and cooling value. And so we didn't necessarily see this too much because we're still just starting working with a single zone model, because I think it's the best way to show you guys the capabilities right now. But of course you can model multi-zone, you can build multi-zone models in Honeybee, but the results are always going to be reported by each zone. Whereas with a detailed full HVAC system, a lot of the times you might, you'll get one heating and cooling value for each HVAC component. So if you have a central HVAC system, you might only end up getting one value for a zone that has a model that has 10 zones, say for example. So that's another distinction. Another really important one is that the ideal air system is, it's modeled with just the hot or cold air instantaneously appearing in the zone. So there's not really, there's no fan to push the hot or cold air into the zone. There's nothing, it just instantaneously just appears, which is why we call it sort of ideal air, that we're not really modeling how that air is created at all. Whereas the detailed full HVAC, it's going to account for how that heating or cooling is delivered to the space, whether it's a box like a fan box that blows hot air in, whether it's a chilled beam that might radiate heat or cooling to a space, or whether it's a radiant slab that that might be heated or cooled, and that then cools down the rest of the space. So this is all being modeled in a detailed full HVAC system, whereas it's only just this ideal air that's appearing in the space for an ideal air system. And then finally, so that kind of goes without saying that there are no fans or pumps or anything in an ideal air system. You never get the energy used of fans or pumps through that way. Whereas detailed full HVAC systems, you're going to get that energy consumed that are needed to deliver that heating and cooling to the space. All right, so those are just some key differences. Now I want to kind of impart to you guys some of the knowledge that that I've learned in working between these two systems, because I know there are probably a lot of people on listening here who maybe have only worked with ideal air systems and may say to themselves, well, why do I really need to model a detailed full HVAC system? What am I really gaining by that? And vice versa, there may be some people, especially if you're coming from an engineering background, you may never have actually built a model with ideal air systems, because every model you've built has a full HVAC system, and you might not necessarily see that there are sometimes some benefits, especially in terms of visualizing some things with running ideal air systems. So just to explain those quickly, and to explain sort of what you can and cannot do with each. So both of the ideal air detailed full HVAC systems, you can model a big range of HVAC strategies, like economizers, which mix in sort of outdoor air to cool the space, heat recovery, which you guys may remember we did last time, humidity control. All these things can actually be modeled with both systems. And yeah, just to really point out from last time that heat recovery, we tried out this strategy. We saw that effect on the energy balance just using the ideal air system. So you don't necessarily need to model a full HVAC to get a sense of how it's going to change. And demand-controlled ventilation, only ventilating when people are in the space. We also tried that out with ideal air systems last time. But now that I say this, though, that there are actually, several strategies that you can really only model if you have a full detailed HVAC system. So things like higher efficiency fans and pumps, the ideal air system doesn't have any fans or pumps, so you can't really model the effect of those. Or better boilers and chillers, something that we're going to look at today where you separate the loads, what it takes to heat and cool the space from what it takes to ventilate the space. That is often associated, the separating of those two is associated with a lot of energy savings. You can't really model that with an ideal air system. Having different, separate HVAC systems for different types of programs. Because sometimes if you have one program that wants to be heated and another that wants to be cooled, that can create inefficiencies, but you can model the benefit of that by using a full HVAC system, and different sort of supply water temperatures. So we can change the supply air temperature of the ideal air system, but that water temperature of usually that hot or cold water that is used to heat or cool the air. You can only model that with a full HVAC system. And so now, I mean, just to sort of say, like, when is the assumption? When is it okay? I mean, knowing that we can't model a lot of these things with the ideal air system, when is it okay to use that? And I'm just going to show you what the general knowledge that I found in my experience of applying both of these types of systems to design problems. And sort of this is the general advice that I'll try and pass on to everyone here. I mean, the first thing is that you can use the ideal air assumption when you're looking for visualizations of building energy balance, or you're calculating, you just want to get a building balance point in order to be able to understand, for maybe some other simpler types of studies you need a balance point. For these types of visualizations, I mean, you kind of have to run an ideal air system, because if you want the energy that goes into your building equal to the energy that goes out, that heating or cooling has to be the energy that is added or removed from the zone. So if you need, and hopefully you guys have gotten a sense from last time how these visualizations of energy balance are helpful, and how they can lead you to, okay, I want to change this strategy affecting the mechanical system rather than the envelope. The envelope's pretty good, and so forth. So when you're trying to generate these types of visualizations or get these types of numbers, that's the ideal air system is okay. Secondly, you have to, if you're going to use an ideal air system, you can't be too concerned about how much more valuable heating is than cooling. Just because you're only sort of you're only modeling, you're drawing the boundary around the building, really around your zones, and you're not really modeling an HVAC system or modeling anything else that will affect how valuable heating versus cooling is. And so this can be, I mean, just to warn you, the cases that have been most difficult with me is that you have some types of heating and cooling systems that they have wildly different values. It's like it can be much more difficult to heat a space than to cool it, or vice versa. It can be much more difficult to cool a space than to heat it. And so be particularly careful with, if you have, let's say, a whole HVAC system that is using ground or lake source heat pumps, it is usually much easier to cool a building down, when you have this big reservoir of, let's say, cold water, like lake source this lake source cooling system for Cornell University. I mean, in that case, you really want to focus much more on reducing heating rather than cooling. And if you only are modeling the ideal air system, you're kind of looking at both and not really treating those with different sort of weight. And so you'd really want to kind of model the full HVAC system if you're using something like ground or lake source cooling. Similarly, if you have a heating system that takes advantage of waste heat, like a combined heat and power plant, where you're generating electricity and then all that waste heat that is not turned into electricity you're using to heat your building, that can wildly shift the equation in the other direction, where you actually care much more about minimizing the cooling energy than minimizing the heating energy, because you have this free heating available. So just be careful if you're using the ideal air assumption that, it's got to be at a point where you're not worried. You're just generally trying to reduce heating and cooling together, or something, or you already know that, that you're only trying to reduce heating or you're only trying to reduce cooling. That you're not trying to weight these against each other, because the ideal air system won't really give you a good sense of that. So that's another point. The ideal air system assumption is also okay when if you don't need metrics like utility bills or energy use intensity, that's because you can't really get the costs that it's going to take to heat or cool the building from an ideal air system. You can maybe get a relative sense of it by the change over a bunch of different strategies. But really, if you need a metric like utility bills or energy use intensity, you should just be modeling, the full HVAC system. And then finally, one that I'm just going to say is not too well known out in the field yet, but one that I've kind of learned the hard way. One of the cases where you really shouldn't use the ideal air assumption is when you're using your final intended HVAC system isn't air-based. So, for example, a very common thing that we do these days throughout practice is that we'll put these like hydronic tubes filled with hot or cold water. We'll circulate hot or cold water, and we'll cast these into a slab, and we'll just keep that slab heated or cooled. And when you use this type of system, when you're heating or cooling the space by heating up or cooling down a slab, it is just a completely different set of building physics that govern this type of heating or cooling, as opposed to an air-based system where you're trying to deliver hot or cold air to the space. And I kind of learned the hard way. I mean, luckily I caught it in time for a project where this happened, but where I was using an ideal air system to start off with, and we were ultimately going to use a radiant slab system, and the effects of different strategies were just much different for a slab system than for an air-based system, which is really what an ideal air system is. It is air-based. It's delivering hot or cold air to the zone. And so just to give you guys a sort of sense of this, I mean, you don't have to read too much into these graphs, but this is just comparing a scenario of fan coil units, an air-based system, with a radiant slab system, and these are the same set of shading strategies for this one type of space that I'm looking at here. And clearly you can see that the air-based system is affected much more by these shading strategies than the radiant system. And I'm very glad that I caught this, before moving too deep into design. But I mean, the moral of the story is that if you're going to use a radiant slab, you kind of need to make the decision earlier in the design process to know how to model it well. Just make the decision of whether you're going to have a radiant slab or make it air-based. And radiant's great, by the way. I mean, you can use very low supply temperatures so that you can pull hot or cold water from different locations that aren't, are out of the norm. There are a lot of great, and I've many simulations I've run of comfort show the radiant slab being more comfortable a lot of the time. But just you really have to be aware of the assumptions, and don't use an ideal air system to represent a radiant slab system. Just model a full HVAC if you're going to use a radiant slab. Okay. All right, so with all these four sort of do's and don'ts of ideal air systems, I'm going to jump now into actually comparing now. Starting off with sort of the file that we were working with last time, I'm going to jump into actually doing some grasshopper work right now. So Arvin should have sent out the files that we're going to be building today, the sort of HVAC definitions and comparisons that we're going to be doing. But basically, I mean, you guys should recognize this is the same exact thing that we worked with last time. We're modeling a single zone of an office building. Right here, and we haven't been too worried about the context because I'd really rather just should focus on all the things that we can do on this one zone level, so you guys understand the capabilities on the single zone. And once you get that, you can really extrapolate this up to build bigger energy models. So all right, so we have this one zone of an office. We started off with it being all glass last time. But we reduced that. We put a bit more glazing on the south than on the east and west. We combined all those surfaces together into a single zone. We put in a better window with a better U value on this zone. And again, though, but you guys remember that at the very last part, we started to get into HVAC systems where we put in some heat recovery, we put in some demand-controlled ventilation. But importantly, everything that we were doing was with the ideal air load system. And maybe actually I'll just run this right now, this initial model. So if Arpin should have sent this out, so you guys should have this file, the workshop start file, which is really just a condensing of what we worked with last time. And you see that we get out of the model, we get out some cooling load and heating load in kilowatt hours here. And maybe just so that we have a comparison, let's see, what's the best way to do this? Maybe I'm just going to copy some of this data and internalize it, so we can start to actually just compare what we get with Honeybee when we model ideal air versus a full HVAC system. So we're just going to start off by straight up going straight to the heart of the matter. So I'm going to internalize that data just so that we can rerun the simulation. So all right, so these are going to be our ideal air results here, and now I'm going to change it to be a full HVAC system here. So you'll see this component that I got here, that I have here on the canvas. It's a Honeybee component. It's just this HVAC systems list, and really all that this is if you hit the little arrow here, this is the list of all the HVAC templates that are included in Honeybee right now. And just to give you guys a sense of where all these come from, especially if you're not aware of some of these system types, systems 1 through 10 are baseline systems that are published by ASHRAE, by the American Society for Heating Air, well, the Engineer Society for America. sorry, I can't remember the full acronym right now. Maybe I should have got more sleep. But in any case, so systems 1 through 10 are baseline systems. That are really, these are the systems that are most building stock these days. In the U.S. at least, will have these types of systems. And you'll see actually if you hover over the HVAC systems input of the component here, you'll see that there are recommended different types of systems for different types of buildings. So residential buildings usually will have a systems like one or two, which are very simple, sort of packaged air conditioning, and with like a simple boiler with some radiant heat, some what you'd probably commonly see in a lot of residences in the U.S. Whereas the other systems are mostly made for more commercial use, where you have sort of packaged single zone systems for non-residential 3-4 buildings, all the way up until when you get to like large office buildings like what we're trying to model here. You'll use system 7 or 8, which is a variable air volume system, or VAV system. And that's actually what we're going to model right now because we're modeling a kind of large office building. And then finally you have sort of a warm air furnace for systems 9 and 10, which are really only for like warehouses and storage spaces where you're not going to cool the space or you're not going to air condition the space. So that's important. So systems 1 through 10 are kind of explained here. And it's just the 4 other systems that we have here. These are common systems that are being put in these days that are usually being put in to reduce energy use. And importantly, all 4 of these systems have what's called separation between ventilation and thermal loads. And I'll explain that a little bit as we get into visualizing the HVAC systems. But importantly, the most important thing to remember is that systems 1 through 10, all of them, when they deliver hot or cold air, they deliver it with just a single system. They're trying to both heat and cool the space with hot and cold air and deliver the minimum amount of ventilation to keep, to make sure that the occupants don't suffocate or get funky smells in their building. So, all right. So with that, I'm going to switch over to system 7, which is a variable air volume with reheat. And we're going to rerun our little office model here, just so that we can understand the difference between an ideal air system and a full HVAC like what we're modeling right now. And what you can initially see is that, all right, let's compare these two. So you'll see, first comparing, let's just look at the cooling between the ideal air system, which is on the right here, and the full VAV system, which is on the left. So the first thing you'll notice is that this is the name of our zone. If you guys remember from all the way back here, where we named our zone back here, we called it Boston office. So that's what the first thing that you're seeing here. That it's a zone by zone basis that you're getting this cooling energy and the heating energy too. Whereas when you're modeling the full HVAC system, you're getting this for there could be multiple chillers in your model, but in this case there's only one, and we're getting cooling electric energy for that chiller coming out of this component, as opposed to just that heater added or removed from the zone. Another thing that you guys will notice is that even though, generally we're seeing similar trends, like we're not cooling too much in winter and we're cooling a lot in the summer, but importantly you guys will notice that a lot of the times the cooling energy of the full HVAC system is less than that cooling energy of the ideal air system. And the reason for that is because for every unit of electricity, you're usually able to remove much more heat from the zone with that cooling system. So a lot of the times, and the ratio of that heat removed from the zone, the heat removed from the zone divided by the electricity needed to run that chiller, that is called the coefficient of performance. And so that's why you don't see exactly matching values between these two. And again, we're also seeing something similar happening on the heating side here. That, as I said, the heating is for a single zone. So just like that, whereas in this case this is for a boiler that we're actually getting this heating energies. And importantly, you're also seeing that even though both these, both units are in kilowatts also, just to be clear, but we're seeing that the boiler is usually using much more heating energy than that which is simply added or removed from the zone. And that's because you oftentimes need more fuel. Not all of the heat contained within that fuel can be turned into heat within the space. That there's some of it that goes up a chimney or flue, and there's some of that heat that's going to get lost. And so that's why we're seeing, that's why we don't see exactly matching values. So importantly, though, the very nice thing about now having these values in Honeybee, and I just want to check to make sure that we're going through these in the right order. All right, so we discussed a little bit about, and we're going to compare some HVAC templates in a second. You know what? Actually, let's just do a comparison straight up here. You know what? We'll do. All right, I'm going to show you guys something first before we get into actually looking at what would happen if we used a different type of template HVAC system. And the thing I'm going to